In this tutorial video, I will introduce QPCED3, a computer software for quantification and processing of polycrystalline electron diffraction patterns. The current version is 3D. This is one of the main components in the Landyne software suite for electron diffraction simulation and crystallographic analysis. You may download the software suite from the website on the screen. A paper about previous version of QPCED3 was published in Journal of Applied Crystallography 2012. We already showed the installation of Landyne Suite together with the Java Runtime Environment and the Java Advanced Image in the first video of the series. You can find it on YouTube by searching for Landyne plus Launcher. Please refer to that video to install the Landyne Suite on your PC. The higher the resolution of the monitor, the better to run the software. My laptop has display with a resolution of 1920 x 1080. Here is the Landyne Launcher icon. Double-click this icon to activate the launcher. If you have a license file, please copy the license file to C folder, Landyne 3 program. This is the software QPCED. This is license key. Click this button to start QPCED. You will see interface like this. A license dialog may pop out in case you don't have a license file. Then you should select the demo mode to continue. Let me briefly introduce the function on the menu bar first, and then go to detail with the example later. File include load electron diffraction pattern, load electron diffraction profile, save the analyzed result, exit. In process, this is pattern adjustment. You can resize the diffraction pattern you load. You can align the incident beam to the display area center. There is circles for guide you to do the alignment. This is ellipticity. You can check the ellipticity in diffraction pattern. If you need correct them, the program can do the correction to make it a full circle. This is enhancement. You can display your diffraction pattern in different pseudo colors, or you can find out strong and weak diffraction ring by use the maximum intensity profile. And there are various of display method here. In pattern, the first choice is ROI and TIFF. ROI is region of interest. After you resize your image, center the image and also correct the ellipticity. Then you can save the image by choose the size. Now we put 600 here and you see the square. You can remove this one away. Inside this area will be saved. You can choose different TIFF PPI, means point per inch. Usually it's 300 or the number is larger than 300. Then you can go to save the diffraction pattern in TIFF. If you choose save the image in JPEG, the resolution is not affect the image, only the size. Quantify. And the quantify, this is the main functions in QPCED. First is calibration. You can use the scaling bar to do the calibration. To convert the 2D diffraction pattern to a profile, you can convert the pattern to a line profile or along one selected ring to show the intensity profile. Then there are two ways to search for the background and subtract it. This is for the peak analyze to find perfect match for the peak function. And you can adjust the overall height of the peak. You can also do the intensity normalization. After you get the intensity profile, three types of profile you can save. You can save the electron diffraction line profile. It's in blue. You can save the integrated profile. And you can also save the neat peak profile. We'll explain each of function later. Option provide you to hide the graphic menu bar or show. You can use one of the three window style. In help, it gives you a function of current drive and serial number. This is the serial number. You copy this number or take a snapshot of this dialog and send to us. We will prepare the license file for you or use the serial number. Current version is 3D, is updated in November 2017. You may load the electron diffraction patterns, use the window file system. In experiments, QPCED, click here. You can also use the drag and drop function. Then you had first find where the diffraction pattern is. And just hold mouse left button, drag, and when you see the move, drop it. Get the same pattern here. Then we need to resize the pattern, slightly adjust the pattern. And also align the pattern, move the incident beam right in the display center. You click this slide bar and you can use the arrow key to move up and select this one to move left and right. And you can choose to show or not show the guide ring. You can change the ring radius. So now the pattern is perfectly aligned. You can check all the ring. After careful alignment, we can see the two profiles, the blue along the blue line slightly outside compared to the red peak. Both red peak are slightly inward and blue peak outward. We use the radius mark to measure these two peaks in pixels. Suppose this is for the blue one is larger, we shall put the longer axis here. That will be 142. And we reduce this one. That match the red peaks, so the red peak will be 141. in this case, we don't have a tilt angle. Later we'll show when we tilt the angle what happened. Then we can calculate the ellipticity. This one gave the number is here. The tilting angle is 0, so azimuth also 0. So we can correct the pattern. After we correct the pattern, you can see the red line and blue line are in the same radius. So the pattern is now in perfect circle shape. When we make alignment, we make sure the horizontal and vertical profile in exactly 0 and 90 degrees. But when we do the ellipticity correction, we can tilt these two skin lines, as I demonstrate here. In the same time, you can see the profile along these two lines are changed. Since after we correct it, now these two peaks are perfectly matched each other. You can see here, I make it back. If you use any tilt angle here, you should copy the azimuth here. Longer axis is always longer than the short one. The azimuth is how much you tilt from the horizontal line to the longer axis. If it's counterclockwise, it's positive. If it's clockwise, it's negative. If you want to do the correction again, you can undo what you did before. Just click this button. Before to output your image, make a correction on the ellipticity. You get a perfect pattern and you can use it in your publication. You can use the ROI and TIFF output your image. We'll go to detail on this later. This correction can be done for the ring pattern. Can also treat the diffraction pattern from single crystal. Those are from the same microscope, same condition. So calculate the ellipticity and use that number for all the patterns you get from the same microscope, same condition. In summary, if the diffraction stigmation in TEM has not been fully corrected, distorted experimental diffraction pattern will be recorded. QPCED3 can be used to check and correct the distortion in diffraction pattern due to the stigmatism. Of course, the more important thing is to correct the diffraction stigmatism in the TEM. The second application of QPCED3 is to enhance the diffraction ring with a marker and the pseudo colors to make diffraction rings more revealing. This profile is created by the most strong point in the ring. And this is just invert the colors patterns. Choosing other colors, you can get this black body pseudo colors from most strong one to relative weak one, and it's more attractive if you use the pseudo color picture in your poster and papers. This is the original pattern. And this is the rainbow pseudo color. You can also adjust the brightness and the contrast, just like most image processing software did. This profile can be shown or not shown here. You can also show as a curve or dot. Curvature is more revealing. You can track down all the beam by tracking the beam and click. That will add a ring there, and track this one. And this is add another ring. By this way, you can mark all the weak ring. You can also delete them if you make a mistake. Check, delete, and tracing to the line, click, that will delete that ring. You can show the ring in different colors. After the correction and enhancement, we want to print out the diffraction patterns. You can show the enhanced line or remove them. In pattern, first is ROI, then is the teeth. It's a PPI, is a point per inch. This value usually set to 300 or up. We can show the ROI square. And here we type. And you can see a yellow square appeared. Only inside yellow square the image will be saved. if you go to pattern, save the pattern as T, or you can save the pattern in JPEG. In the JPEG format, only the size defined inside the square, but the PPI will not affect to the image. We can also remove the horizontal line and vertical line. In here, you see more clearly about the yellow square. Here, you'll remove the horizontal and vertical line. The next is the main application. To quantify diffraction ring pattern. We can get the intensity distribution along the selected ring. This is used for detect any implant texture. We'll choose this one. The second one is integrate the intensity along the ring and find the distribution from the center along the radius. We'll first do calibration, then we'll do along the ring, then do the whole pattern. The calibration dialog is in quantified. We also need the adjustment dialog, which can show and adjust the guide ring. Now we have the green ring selected, the first ring, and it reads as 141. We type here, and we know this is FCC aluminum. The first ring is 111. The D space is 2.3381 angstrom. And then update. That's the calibration is. We may select one of the ring and get a profile intensity distribution along the selected ring. First, uncheck the guide ring here. Go to quantify, pattern and profile conversion. And this is the ring. We have a radius and width. Show you the width. This is large, and this is the smaller one, suitable one. And we can choose the radius. For the first ring will be this one. Then make the convert. And here you see is random distribution is the height of the intensities. If we have a in-plane texture, the intensity will drop at a certain point. And this show is fully random distributed ring. Let me show you get the second ring. Let's see the intensity distribution along this ring. Go to convert. So this will be the second ring distribution. Same thing that you can get the other rings distribution. The profile of integrated intensities along the radius can be generated. We need a selected pattern, then click on the convert. Let me first show you how the beam stop works. The beam stop here will simulating in the real experiment if you have a beam stop on. Here both orientation and the width are 0. Let's increase the width. So you can simulate how large the beam stop in your experiment if you have beam stop on. And here to show the orientation of the beam stopper. Since we don't have a beam stop here, I can turn this one to 0. To remove the effect of the incident beam to the intensity profile, we need to go back to the pattern adjustment. This is the profile along the horizontal and vertical line. Now we go back to this dialog. This is the radius of the incident beams. We're going to increase it. So you can see from here and also from the brief profiles here will be cut off in the patterns. There are no information of intensity distribution inside this disk, so we can make it even bigger. Here this line is tracking down how the incident beam affected to the distribution of the ring. So we have other 3 parameters: the height, the full width at half maximum, and the ratios to simulating the position of this line. Try to close as possible to these curvatures. So the background curvatures best simulate on lower part. We can increase the cutoff. By now, the most part of the effect of the intensity distribution is covered. Then we can do the convert. And you can see this line is intensity distribution from the center to the side after we remove the effects of the incident beam. Now we're going to define and remove the background intensity. Let's go to quantified background. And you see the intensity profile is transferred to the main display screen. And we can lift the intensity up. Go to peaks, lift up. There are two ways to define the background intensity. The first way is called the Bruchina method. The only parameter is step and try and to see how it fits to the background. The second way is linear interpolation method. Define point. The point will be joined together to form a curve. We just try the first method. This curve shows a little bit over, go to the peaks. Let's try 50. It looks much fine. Define the background intensities and remove the background. Now we have the pure peaks here. Next step is define the peak positions. Here you have an automatic search method, or you can identify manually by clicking on the top of the peaks. We try to search, and here it gave us 7 peaks. 1, 2, 3, 4, 5, 6, 7. There must be one peak defined more. 1, 2, 3, 4, 5, 6. Only 6 peaks, but here listed 7 peaks. Let's try to see where the one peak we may need to delete. This one look species is the height only 1. Position in 646, and here are the position to show 650 around here. So there are a small peak defined here, which is certainly is not true. So we selected, we can delete number 6. It didn't affect here because that peak is very small. Delete, you can delete here and select the peak, or you can delete from the table. If any peak you didn't find, you can add also. So there are many ways edit how many peak you selected. Is the peak correct or not? Next, we have a refine the peaks. We have a two peak function. It's a pseudo Vogel and Pearson 7. You just try the first one. Always try the first one. If it didn't work, try the second one. We'll click here. Refine the position and also the height. It calculates the despacing too. Also use the calibration we defined earlier to calculate the despacing. Still the intensity not defined. Here we have a right click of the mouse. We can show the peak as a bar or overlap superposed. And you can see it defined the peak perfectly. And this one you see is a little lower because there are superposed. And this one also lower. The last one is show the overload composite. They will trace the experimental data perfectly. So normally we just show the second one, overlap superposed. If the refinement is not going well for some special case, you can always do the adjust by one. So you click here. You give the position, height, and its full width at half maximum, and the ratio of Gaussian and Lagrange ratio. And you can choose which is the peak number. Here it is. So this is rarely used, but you can define them. After refinement, we can get normalized intensity and also the lattice spacings. Could quantify, normalize the peak of the intensity. This peak is 100, and the rest peak are shown here. We also get the lattice spacing here. To show the overlap computation, we can see the difference of calculated one and experimental one here. The difference is very small, close to the horizontal line. The quantitative data analyzed for polycrystalline electron diffraction pattern can be used in combination with the PCED3 to do the semi-quantitative analysis. And you get the experimental result here, and you do the simulation with the PCED3. Thank you for watching. Please check our other videos about Landyne software suite for electron diffraction simulation and crystallographic analysis.